So it is my great pleasure today to present to you Professor Maxime Heritier. He was very kind to accept an invitation to give this lecture. Actually, he was visiting Greece a couple of months ago, if I remember well, and we tried to organize a live lecture and presentation, but it didn't work out, so we decided to postpone it and organize this teleconference. Professor Heritier is an archaeologist and historian. He is specialized in construction history and archaeometallurgy. His works deal with metal production and trade in the Middle Ages, as well as constructive techniques, with a material and economic approach of great medieval building yards. He received his PhD on the use of metal in Gothic architecture from the University of Paris 1, Panthéon-Sorbonne in 2007. And he is currently an associate professor at the University of Paris 8 at Vincent Saint-Denis and ARSCAN CNRS laboratory. In 2019, he co-edited a book on ancient building maintenance and long-term conservation practices. And since May 2019, he coordinates the metal work group for the scientific project on the rehabilitation of Notre-Dame de Paris, funded by the French National Scientific Research Center and the French Ministry of Culture. The topic of his lecture today will be on that activity. The title is The Iron Skeleton of Notre-Dame de Paris. And it is my great pleasure to give the floor to Professor Heritier. Let me stop sharing my screen so that, okay, so that he can share his screen. We have a good view of your screen, and we are looking forward to your lecture.
Well, thanks a lot, Dr. Gantes, for this presentation and for this invitation to present these researches on Notre-Dame. And thanks to all the organizers of this conference. I was sad we could not give it in Greece, but then again the live lecture might have been a bit simpler. So I will try to first give you an overview of the context of this research, as Dr. Gantes has said. So I'm trying to, yes, it goes. You all know that there's been a huge fire in April 2019 in Notre-Dame, and ever since in the following days, the following months, there's been a huge gathering of researchers on different fields of research, and the institutions, the CNRS, the Ministry of Culture, they've really fast started to organize and fund a scientific program. So the aim of this program is to develop studies on these archives, these materials archives. On some of them, they've disappeared with the blaze. Some of them are really damaged, but others still exist. And also immaterial questions about something about the emotions that have been generated by the fire, also the sound of Notre-Dame, which has been lost because of the fire, and which has to be reconstructed. So many things, many fields of research, different fields of research with multidisciplinary approaches and techniques. And so this scientific program has been organized on 9 monographs on the different materials, but also sound, digital data, and immaterial conceptions. And so it's about 50 labs, about 2,000 researchers on different, very different fields of research, from art history to digital analysis or geochemistry, and many different things. So in the time of restoration, first to help the diagnosis for the architects, of course, because some materials were alterated, but also to have more fundamental research on history, climate, on the monument and the knowledge of the monument itself. So the work I'm going to present alone today, but it's really a collective work, and so this is the metal work group I'm leading since the 2019. So as you can see, with about 15 colleagues, which are working on really different topics from history, archaeology, but also on dating, archaeometry. So we'll have all of this, and so I want to insist on the fact that this work and what is going on today in Notre-Dame is really also a collective adventure, and that's helping me to present today. So to go back now to the topic, I'll have a brief introduction about the use of iron in construction in medieval times and in the Gothic period before going to Notre-Dame really quickly, because it's not obvious that this metal was used in such architecture, and it was not always obvious. There's many debates that go back as far as the Middle Ages between architects who fight about the use of iron in Milano, for example, in the 14th century, but also other architects or art critics like John Ruskin in the 19th century, who are really despise this use of iron, which is made by certain builders, and for which the true architecture, as John Ruskin said, does not admit iron as a constructive material. So this kind of thought has engendered some dramatic restorations, such as in the 20th century in Beauvais Cathedral. Some of the medieval tie rods, they were removed because they were considered as ugly additions of the 19th century. It was just afterwards, some decades afterwards, that we understood that these tie rods, they were actually the medieval tie rods that were taken down. So work which has been going on, particularly a bit before my PhD, but then my PhD contributed to this knowledge also. Really insisted on the fact that iron had indeed many uses in Gothic construction. First is to hold the stained glass windows. As you can see here in Rouen Cathedral, you have bars of iron that are that you cannot make the stained glass window hold without these different bars. So there's hundreds of tons per bay, and dozens of tons of iron which are used in the greatest cathedrals, but also it has a structural role in many cases, not with glass, but also with stone. And what is best known so far, what was best known so far, are the great cathedrals of the beginning of the 13th century, such as Bourges, such as Chartres, which you can see here. And so we discovered, and we could insist on the fact that tie rods of iron or series of staples of iron, like here in Chartres, these tie rods here in Soissons, or these tie rods which are here above the aisles of Bourges Cathedral, were implemented during construction to help the stone structure to keep up, to maintain itself. So a really structural role ever since the great cathedral's construction in the beginning of the 13th century. Also sometimes in the form of iron chains, which sorry, which are hidden sometimes in the masonry, such as in the Sainte-Chapelle in the middle of 13th century, or here in Saint-Denis in the upper walls. hidden just above the stained glass windows. Or here another example of chain in Bourges, which is not really hidden, but which cannot be seen when you visit or when you enter the cathedral. So I will not develop all these uses, but that is so far what we knew of iron in construction in the great cathedrals of the 13th century before working on Notre-Dame. So going now to Notre-Dame de Paris, just a little bit of chronology. Here we deal with a cathedral which is a little bit earlier than those we spoke of before, because its construction started in the middle of the 12th century in the years 1160 to be precise, and it lasted until the middle of the 13th century. It was also strongly restorated in the 19th century, so it's a very important point for Notre-Dame. And I'm sorry, I'm hearing, yeah, I'm hearing some voices. Sorry. And one point which is important is also the dimensions of the cathedral, which is at the time it was built, the first one to surpass 30 meters height for the vaults. So it was the biggest, the highest cathedral built at that time, not the widest, but almost, and one of the longest too. So the dimensions, if you compare them to the cathedrals which are coeval to Notre-Dame in the middle of the 12th century, it's not the same size at all. So that's an important point too. Yet, what we knew before the fire about the implementation of iron in Notre-Dame was not much, and it was mainly thanks or due to the 19th century restorations. So that is basically what we knew. We knew that in the middle of the 19th century, Lassus, the architect Jean-Baptiste Lassus, implemented some iron tie rods, chains in the upper parts of the core, just above the checkered cornice, which is here, which you can see here. It's on this part of the cathedral, circling the core. And that these chains and tie rods of iron, they might have replaced a former system that is described by Viollet-le-Duc in his dictionary of a series of iron staples that were inside the cornice. So we still do not precisely know if these staples are still here or not, but as you can see, many blocks have been changed. So it's likely that one system has replaced the other. And that was it. That was the only information we had about iron in Notre-Dame. And after the fire, it became obvious that there were many, many more uses than that. It was also the fact that we could access the cathedral thanks to the access that were granted to researchers. And so series of staples that could not be seen before were discovered. You can see here the upper walls. Under the burned framework, the framework was placed on those walls, so it would not have been discovered, this series of staples, without the fire. Also, the inner structures of some decorative elements, such as crestings, and many other elements from the upper parts, nails, pins, bolted rods of different size, and from different conceptions. You can see here elements which are which were made in industries other that were forged, so different time also for these iron elements. So one of the questions that was sorry, ours was first to understand and to document, investigate the use of irons in Notre-Dame in its structures and how it evolved from the Middle Ages, its first constructions, and throughout the restorations and repairs, notably that of the 19th century. So that's what we're first see are in this presentation are these uses of iron in Notre-Dame. And then I will speak about the other investigations on these elements which we have discovered. So one of the first impressions that we had when we tried to first scan the building looking for the use of iron elements is the importance of the use of series of staples. So we saw those before on just below the framework. I'll go back to that a little bit later. But in the first levels in the tribune, so in the about 10 meters high above the great arches, these series of staples, which were clearly visible before, they had never been documented, investigated before that time. And what we can see is that there's a really regular pattern in the core, in the nave also, although some places are currently cannot be accessible, but that we have these staples which are sealed with lead, which are double series of staples, such as the drawing of Viollet-le-Duc, and which are placed above the arches, the main arches in the tribunes. So we see that we have different sizes for these staples. Which means probably that I mean, they're not all coeval because the core is a little bit earlier, was built a little bit earlier than the nave, so there might be also differences in the northern nave and the southern nave, so maybe different supply, different workshops working there. I'll go back on this point earlier. So, but as soon as the first levels of Notre-Dame, we have this series of staples, hundreds of staples, which are about 2 kilograms each for these, 50 centimeters long, and so that's about 1 ton of iron, maybe a little less. We could also access this part just under the terrace of the core, and we also noticed that the same series of staples are also visible in this part. So this is quite difficult to access this place in the building. We'll need to we could take advantage of the fact that some of the terrace slabs were taken down for restorations, but there's we could document the fact that all these walls they're clearly attached. The blocks of stones are attached with staples. Other staples used for in the nave this time to attach some of the magnificent monolithic column blocks which decorate this part of the structure. So here we have blocks which are really tall, from 3 to 4 meters high, and only 15 to 20 centimeters in diameter. So it's really thin. So they need to be attached to the masonry so they would not fall apart. And so they're attached by staples which are almost invisible, but that could be discovered using a metal detector. And one of them would also taken down thanks to the restoration. So here, smaller staples, of course, than the one we saw before, but still a massive use in the nave. And then we come to the upper walls and the series of staples that were unknown before the fire because they could not be seen. And we had the chance before they placed the provisional roof, which is now in place to protect the building, to be able to measure and to sample some of these staples on site. So that's a really regular pattern, about 600 staples overall. It's the same, it's a double series of staples, about also 40 to 50 centimeters long, but a bit thicker. Those, they're about 3 to 4 kilograms each. So it's about 2 tons of iron which are used in this place. And if you can see here what we could observe at that time, there's some parts that were inaccessible, and we'll have to wait the restorations to document this, to investigate on this part. We can see that there's only one staple in the core, in the round part of the core, and there's 2 series of staples in the other places. So there might be something happening here in the construction patterns that we will have to try to find out when it's accessible. So as you can see, the use of staple, which is an ancient form which is known since antiquity, but which is massively used in Notre Dame's construction to help to block some of the stones together. We'll go back to this role a bit later. There are many more uses of iron. In the base here, you can see the traces of ancient irons that were, the stained glass pattern has changed much since the Middle Ages. And so there's been several restorations. And so these tyros, they were cut at one time. We don't know when they date from, because there's no investigation on this. It's currently undergoing, but they're probably from a modern, or maybe the original tyrods of the medieval times. There's also some pins in the masonry in the different parts of the tracery, the stone's tracery. Pins are also used regularly to maintain the blocks together, and as you can see, all this is also sealed with lead, with lots of quantities of lead, which are also important in the structure. We also have bars used to attach some statues, to attach some columns in many parts of the buildings. Also hooks, which here are probably early modern, maybe 17th, 18th century, to attach the decorations, the paintings here probably. Many different uses also discovered, and that was one of the discoveries, is the important number of nails that were found thanks to the excavation, the archaeological excavations of the burnt remnants of the upper parts that had fallen down on the vaults, and that were taken down with noting each zone, so that we could replace each artifact that was discovered in the place where it was found on the vault, so to help understand where it could have placed in the initial structure. So here, for example, these small nails here, so that we have nails from really different sizes, from a few grams to almost 1 kilogram each, so different uses also. These small nails, they're only found in the northern vaults, and that's precisely where a wooden pathway, which was part of the framework, was installed. So it's probably the nails that were used to attach the wooden parts of this pathway. So far, there's more to learn about the nails. I'll talk about this a bit later, also with some analysis. Also, the work on the typology of the different cresting armatures that were found, which are the inner armature of these lead ornaments that were initially placed by Viollet-le-Duc, shows that there were different restorations, and that each restoration had different thinking. Some reused the former Viollet-le-Duc shape, and others changed totally the lead and also the inner iron armatures. So that's the work from my colleagues from the Historical Monuments Laboratory to replace this evolution due to the restoration of campaigns of this cresting that originally dating from the 19th century. And then we come back from these uses of the 19th century with these restorations we've already seen before, implemented by Lassus in the 19th century, in the middle of the 19th century, probably to change a medieval pattern of staples that was present before that. So yeah, I think we did not go through all the uses of iron in Notre Dame. There are some more, but these are the main that could be investigated so far, and the main on which we have already done a bit of analytical work, archaeometallurgical work, or it's undergoing on these elements. Because now that we saw these uses, several questions arise. First, it's what's the quality of the alloys that were used in function of the time they were placed, from the medieval times, modern times, and early modern restorations in the 19th centuries also, and also questions about the supply of the building yard, the fact that iron could have been recycled it was recycled sometimes in the 20th century restorations, and it could also have been before. So so to try to investigate these historical and technical questions on these iron elements that were discovered, and to try also to understand more precisely the phasing of iron implementation from the Middle Ages to the restorations of the 19th century by dating some of the staples of the iron bars that were discovered, to make sure that they are coeval to the masonry in which they are implemented, or that they belong to restorations, repairs that were occurred later than that. So questions about quality of materials, dating, provenance, which uses methodologies that are being built in the laboratories in which I'm working over the past 20 years. So this work could be applied on samples that could be sampled on the monument, or that had fallen down because of the fire. So a few staples, 12 staples from the upper walls mainly, but also from the tribune, some of which were broken, as you can see here, and could be sampled. One column staple also here, this small one, some nails from different sizes, and also elements which we know are from the 19th, 20th century, the cresting and tie rod, but that was questions that were also asked by the architects, so to understand the quality of these elements, if they could be reused or not in the structure of Notre Dame for its restoration. So the protocol, analytical protocol, which was used is to make some metallographic, thorough metallographic analysis on each element, usually making several cross cut on each artifact, and then to analyze some impurities which are called slag inclusion. I'll detail that a bit later. later, to understand their major element and trace element composition in order to have information on iron sources and provenance. Also radio cable dating on a few samples, not all of them, and also tensile tests to understand the mechanical properties of these elements. So I'll go first with the metallographic analysis on the different artifacts that were sampled. So here you can see the staple of the core tribune that we spoke about earlier. So it's the same here. You have how the weight was cut, and so the surface is polished and etched with the nitrile etching, which helps discover the steely parts, the carburized zone of the iron. So here you can see we have an heterogeneous ferrous alloy with many ferritic zones here, the bright ones, and some more steely parts here, the darker ones. And this band, the band structure here we can see is just normal, because if you have an heterogeneous material and you forge it to a long bar, then the heterogeneities will have a tendency to form this kind of bands in the structure. So it's not intentional, it's due to the forging. We can see that we have structures of Wittgenstein ferrite here, which are typical of rapid air cooling, which was typical for this medieval blacksmithing. So here we have very typical iron, which can be compared to what we have seen in other monuments before. All the small black dots here, they're the so-called slag inclusions. So they're impurities that are principally made of iron silicates, which come from the ore and which are the not unreduced part of the ore, which most of it is expelled from the furnace, but some of it, as the iron is not produced in a liquid state before the end of the 19th century, it remains entrapped. Some of these slag remain entrapped and form slag inclusions in the matrix. So it has an importance for the quality and the mechanical properties of the iron. We'll see that later, but it's perfectly normal for ancient iron such as this one. We can see that we have here some nails which are made of a flat band of iron which is rolled on itself to provide the form of the nail. Other nails are made quite differently because they're here made as a whole, you can see. Some nails here are totally ferritic. This one, on the other hand, is totally carburized. So we have a few carburized microstructures which are usually not dominant in the corpus, but which are still worth noting. If you plot the surface of steel observed on each artifact, you can see that 2 out of the more than 30 artifacts that were studied are actually made of real steel, and the other are whether heterogeneous, and most of them are actually ferritic. But the ferritic does not have to be implied as nowadays what would be pure ferrite iron, because most of this iron, they also contain some high content of phosphorus, which can be here evidenced by etching with another reagent, which is etchant, which is Oberhofer's reagent, which provides the difference here. The bright zones are higher higher in phosphorus than the dark one, and at the mesoscopic scale, but also at the microscopic scale, you can see differences here with what we call the ghost structures, which show microscopic high variations in phosphorus content. So phosphorus tends to embrittle the iron, but also to harden it, such as steel. So this ferrite iron, they're actually sometimes as hard as the steel ones. We did not make some micro harness on Notre-Dame, but we did it on other buildings before, and that's what it actually showed. So there's a lot of phosphorus in many nails and in most staples actually, and also for the 19th century elements. One feature that was interesting also, and that we did not expect, is that in the staples they were systematically welding lines inside their matrix. Here you have a crosscut of the staples, which was made here, for example, on this one, and you can see that here 3 different bits of iron and 3 here also were hammered together to make the final staples. So it means that initially, even if they're not big, these staples, they're 2 to 3, 4 kilograms, which is which could be easily produced in a single furnace, even in ancient times. During the sequence of operations from the ore to the final staple, so there were smaller bars that were assembled together to make these bigger staples. So that's one question: what is the constraint in the sequence? Is it a form of recycling, where we're using scrap metal of smaller sizes and assembling them together to forge this staple? So that's one of the questions. We'll go back to this a little bit afterwards, but we were quite surprised because we never saw that before on any other buildings that we studied so far. So maybe it's also the fact that we had several staples as a whole that could provide this this feature, but it was a really interesting one for us. So I'll first go to the mechanical properties of these ferrous alloys. That was actually something that was asked by the architects, so that they would understand, because they are planning and they will reuse these staples that you see here, those which are in good shape, and they wanted to understand what was their quality, to be able to replace them, to place them again in the structures, and also for the tyrant and the iron cresting. So 9 artifacts and 14 specimens were tested. So with these typical specimens, which were made inside each artifact. We tried to do 2 per artifact, but actually some of them broke before being tested, because you can see that there are many, these slag inclusion, we can see them here, and when there are big ones, it can really endanger the structure. So when we machined the specimen, some of them actually broke. So here are the results of these testing with typical stress strain curves on the samples of Notre-Dame. The staples are here in red and orange, yellow, and the thyroid is in black, and the cresting are in green and blue. So we can see that typical stress strain curve, you have the elastic domain here and then the plastic domain. We can see that there there's a real heterogeneity of mechanical behavior, as all the curves are really different. The Young's modulus is that of iron. It's about 200 GPa, with not much differences between the samples. On the other hand, the tensile strength has much differences, and the cresting, and especially the two cresting in green, which are the 20th century iron, they have good properties, whereas the others, and even the tyrrhode from the 19th century, have much poorer mechanical properties, which are just around 300 MPa, which is really low for compared to modern alloys, of course, but which is actually normal for ancient iron before the end of the 19th century. As you can see here, we plotted this results on Notre-Dame, which is in green, in the typical so-called banana curve of the modern different steely alloys, with the more resistant to the more ductile here, and also compared with Avignon's Pope Palace, Dungeon of Vincennes castles, and also churches from the early modern period in Paris, which were already investigated for this purpose in the past times. And we can see that Notre-Dame is the same almost than what we've seen before on medieval or early modern pre-industrial iron before the development of Bessemer and Thomas processes in the late 19th century, which helped to provide great, much more homogeneity in the alloy that were produced. Only these 20th century cresting are actually inside the curve, which is normal, and hopefully for 20th century iron that replaced during the restoration of the cresting. So here are the results which we have, and what we can see when we look into the microstructure and the fracture zone. And this is really interesting, the role of the welding lines, which we can see here in yellow. We can see that in different parts of the welding lines, we have different microstructure because we have different and we have different behavior because we have different microstructure. Some of it ductile and some of it fragile. Fragile with typical pattern, which is probably due here to the presence of phosphorus inside the matrix, and which embrittles the iron, but also the ductile fractures, which is usually predominant in the other samples, which forms itself around the slag inclusions that you can see here, and which provides some crack points once the material starts to be elongated. So the role of these slag inclusions in the fractures is important. So that is for the mechanical behavior of this material. I will go now with the question of their dating, so that's a method which has been developed in the past 10 years, I'd say. It's been published in 2019, which is relies on the fact that carbon is present in the steely part of the ferrous alloys, because steel is a iron carbon alloy, and so that this carbon, which is actually comes from the time when the iron was produced, and the steel is formed in the furnace during the reduction of the iron ore, is able to date the production of the iron. or the date of the carbon that was used, the charcoal that was used in the furnace to make this this iron. So the point is to make this metallographic analysis, as we've seen before, to discover the ferritic zones and the steely zones, and then to look for the carbon in the steely zones and to sample it with drill, preventing any pollution in these bands. So here, for example, or here on the samples of Notre-Dame, here you can see the holes that were made to get the steel in from which then the carbon is extracted and then dated. So we have some results on 8 samples, mainly staples, but also two nails I'll show afterwards. And this dating, they show that the staples from the tribunes, their dating works with the beginning of construction, which is about 1160, the 1160s AD. They cannot be later than that. So that's a good clue to understand that they're probably were indeed placed at the time of construction in the tribunes. And on the other hand, we can see that the upper walls staples, those which were under the framework discovered thanks to the blaze, they're about 50 years later, younger. And they work with the dating, the new dating of the framework that was collected by our colleagues who work on wood and who place the construction of the nave framework about 1215 AD. The date will have to be precised even a bit more with the undergoing work on wood by these colleagues, but that's the date we have so far. So we have two ensembles with about 50 years shift, which clearly match the actually known construction phases of the cathedral. So now we can maybe reconstruct the different phases and the different uses of iron that we have on the different levels of Notre-Dame, with these staples in the tribunes, which are from the beginning of construction, and then also here some staples which could not be dated, but Viollet-le-Duc says it's the end of the 12th century. So hopefully maybe we will discover some during the restoration, and also these staples on the upper walls, which are from the beginning of the 13th century, as now we could date them. So at different throughout the entire construction of the building, it's the same system that was used, the same reinforcement system for the stones throughout the architect, throughout the construction phases, and so that's really interesting to see this and to understand how they used iron as a reinforcement at that time, and especially for the upper walls, because at that time, if you go back to the Cathedral of Bourges, for example, in Bourges, they're trying at the same time to develop new forms of iron reinforcements, tie rods, chains. But here we stay on the ancient form, the staple, which is known, which is mastered, you could say, and so there's a permanency in construction techniques, which is really interesting. And so here you have the same in a map in elevation. Here the tribune staple, here the one in the checkered cornice, and here the ones of the upper walls. So the three ensembles. One of the questions we're trying to ask also so far is for these upper walls staples, it's why apparently they were only placed on the last row of stone. It's something which the restoration will help us understand if there's more than that. But as we can see so far, it seems that it's only the last row of stone, and also the fact that the framework which was placed here in the core was the second framework, because the core was elevated when the nave the upper nave was built. So originally the framework was on this wall, this part here, and so maybe the use of staples here could have been also linked in the core, because they may be not present in the nave, also to the presence of the framework. So this is something we will have to investigate in the future. There's currently next year there will be teamwork between the colleagues who work on the structure and who can model the entire structure, and to model one bay with the framework, with the wall, to see how it works if you take the staples away, and to understand the true role of these iron staples. The hypothesis we have so far is that it might help the blocks of stone to maintain against the transversal, the sharing forces of the framework, in order for the stones not to be pushed apart, pushed outside of the structure. But this, we will know more about this in a few months, once our colleagues will have modeled everything about this. About the nails, on the other hand, we had the surprise to see that these nails, some of them, from their form, it's obvious that they were from modern restorations, but some others, the form of the nail does not really evolve from ancient times to even sometimes nowadays. They're just forged nails, so and does not move that much. But we can see that we dated two of them. One of the steely ones, the most steely ones, and we can see that one of them was produced in the 14th century, and the other one was produced in the 16th century. And what's interesting is that this is two phases where we have not much regarding repairs in Notre-Dame. There's no great restoration on the framework at that time known so far. So are these recycled objects that were used in later restoration, or are these construction phases or restoration phases, repair phases, that should be discovered and investigated? So that's another thing we will work also on in the future with the colleagues who work on wood, because so far we only had access to the nails that were not inside the wooden beams. The wooden beams, they were all collected and stored in a special warehouse, and it was only accessible for colleagues who work on wood since the beginning of 2022, and now we have the colleagues, us who work on metal, to exchange with them now that they have made their first observations on the wooden beams, and they also saw that there were many nails and pins inserted in these beams, and so to cross our informations and try to document the wood and also the iron elements that are linked directly to them. So there's much more to come about this part on the question of the nails. The last subject I will try to address is the question of iron sources and provenance. So we spoke about the slag inclusions, which come from the production from the non-reduced part of the ore, which form a slag, which is expelled from the furnace, but some of it remains entrapped in the matrix. So as you can see, some of it is sometimes micrometric slag inclusions, and sometimes even millimetric. We have really big ones, so you understand the microstructure. It can cause some defaults in the structure. But what's really interesting in these slag inclusions is that they have inherited some of the chemical composition of the ore, such as some small microscopic information capsules inside these iron artifacts, which can be used for provenance analysis, because some of the elements, not reduced elements, that are present in the ore, they pass directly in the slag and without changing their ratios. So we can use this chemical signature to try to understand where some of the iron come from, or if one iron element comes from a different place than another one, by analyzing really thinly with major element and trace element analysis these slag inclusion. So for example, on this sample that we have seen already with the welding lines, you see there's slag inclusion everywhere, and the first thing we do with SEM is to map the entire surface to analyze all the slag inclusion. And so here you have some of the results of the analysis with colors which correspond to compositional groups, which are determined on the different concentrations of some of the elements, such as alumina, silica, calcium oxide, potash also, which clearly shows that first, here on the lines, the yellow inclusions here, they're due to addings, which were flux, which was added during forging, maybe a bit richer in calcium and in silica, flux, which is usually added to prevent the metal from burning, from oxidizing too much when it's a hot forge, especially for welding, and you have to reach some really high temperatures. And then also it shows that you see here the second area, the middle one, slag inclusions are blue, and they have a different composition, different ratios than the top and the bottom one, which are here in green. So this means that here we have, in fact, a cleft weld. We have inserted the second bar here in the middle inside a first one, which was open in two in order to make the weld. So the bottom and the top material are actually the same, are actually the same one. So there's not three, but two different compositions only. And we can take this further with the trace element analysis. Here we plot. So we take an interest on 14 trace elements, which are mainly rare earth elements from the which are lithophile elements, which during the production and the reduction system, they go from the ore to the slag and to the slag inclusion, and do not go into the metal. So the ratios are kept from during the entire sequence of reduction, and they are not altered by any pollution whatsoever during the chain. So if all the staples would come from a single ore source, we would have here a line. And what you can see here, that we have many different lines showing that we have many different ore sources that were used to provide to supply the iron in the building yards of Notre-Dame. So as there's many elements, and to try to have a global look at these elements, we usually use statistical treatments. We prefer the unsupervised statistical treatments. To make sure that if during the treatment you regroup two different slag inclusions, it's because they have the same composition and not because they come from the same sample. Maybe I forgot to say here that one dot is it's written here. One dot is the analysis of one slag inclusion. So it's the same on this graph too. So we use, for example, hierarchical clustering and other analytical treatments, which actually show the same thing. They show here that we have groupings of different slag inclusions which have compositions which are close. Sometimes we have close compositions which belong to two different staples, such as here the pink one and the yellow one. They have the same composition. Here the black one is alone on its side. You have actually the same picture here with hierarchical clustering, and each line is a slag inclusion also. And these treatments, they show something interesting. First, that sometimes, such as this yellow and pink staples, which are actually next to each other in the masonry, you see they have, which was actually this one also, which is the NS7, which is the pink. You see it has well, two different groups, but also that they share the same two different origins here and here. So it means that the blacksmith had at his in his office, he had iron coming from at least two different sources, and had maybe, would it be randomly, or he picked two different bars from two different origins, and he welded them together to make one staple, and he did the same for the other one. So we did not actually explain the patterns so far, but what's interesting, it's showing that there's gathering in the same place of iron from different origins, and that's many different origins, and that could be then forged by the smith. And so we can see here with the pink and yellow, but also with the other one, this one, the green one, which is about the same also, and has maybe another provenance too. The other picture that we can see is that here clearly we have two different, very different compositions, which means that this blue group and this red one, which is the blue group, is here. It's showing, the two graphs are actually showing the same thing. It's just two views, two different methods of viewing the data. So this is the red, this is the blue that you can see here. They have very different composition, which means they do not come from the same region. And what's interesting is that here we mainly have 12th century staples plus another one, and here we have all the 13th century staples. So that appears to be an evolution throughout the campaigns of construction or in the iron supply. Knowing also that what's interesting is that in the 12th century, the commissioner is the bishop. And when we're in the beginning of the 12th century, Bishop Maurice de Sully is dead, and slowly the chapter of canons takes his place as the commissioner of the works. So maybe these different supply sources, they could be linked to this difference in at the head of the building yard, or maybe to other political or economic reasons. That's what we have to determine now. So that's the point we are now. And so there's a young colleague who's starting her PhD, Mathilde Bernard. She just started, and one of the aims of her PhD is to develop this question about iron provenancing, and so to compare the composition of the irons of the staples we saw, but also many more iron of Notre-Dame. She will analyze many more iron elements than what has been done so far, and to compare them with the composition of the iron slags that were found in several regions nearby Paris or nearby the Seine, to compare and to see if which were already excavated or diagnosed by the some colleagues of the who are working in preventive archaeology, and so to try to reconstruct these trading routes from the sites of production to the building yard of Notre-Dame de Paris. So we know now that there's many different sources of supply, and to try to find where do they actually come from. So that's for it, for the studies I wanted to share with you today about the archaeometallurgical study of the iron skeleton of Notre-Dame de Paris. So just wanted to stress, because maybe I did not do it too much, that these Gothic reinforcements that were found, notably in the tribunes in the middle of the 12th century, they're actually the old dust reinforcement found for Gothic architecture. Maybe 50 years before what we saw in Bourges and Chartres in the beginning of this presentation. So it helps us rethink the way that medieval builders did implement their constructions and use this material, iron, to build their cathedral. And it probably and notably the fact that Notre-Dame is the highest cathedral built in the middle of the 12th century and uses much more iron than any other cathedral before is probably a clue to why this material was used. About the quality, we see that it's usual for the Middle Ages or early modern period, but it's quite far from modern standards. But still, it works in the construction, and that there's much thing to do in work on the different repairs and consolidations throughout the time. And that the study of nails and notably will help better understand the way the framework evolved throughout the years and was repaired. And ending with the many questions that remain on supply, recycling maybe, or assembly of iron from different origins, and that's the undergoing works which will be done in the next years, especially during the PhD of Mathilde Bernard. So that's it. I started the presentation saying it was a collective work of many colleagues inside the group. So I want to thank them, but also all the colleagues who run the scientific program Notre-Dame de Paris, and all the colleagues from the commissioners from the établissement public, and also the archaeologists, the heritage from the Conservation Régionale des Monuments Historiques, the architects, and and the workers on the site who helped to do some samples, and the authorizations we had from all these colleagues to do the work we actually did. So thank you very much, and here a glance of the inner Notre-Dame, inside Notre-Dame, as it could have been seen a few months ago. It has already moved a little bit. The spire is will be is on its way to be rebuilt.
Thank you very much, Dr. Heritier, for this very interesting presentation.